Welcome to Maths with Bob. Today we're looking at mechanics and some of the ideas and some examples in circular motion in the horizontal plane. Now, there are a couple of ideas. One of them is that, well, if something's going around in a circle, there's actually something's basically making it go around in a circle. So there's some sort of force acting, and this is called the centripetal force, center seeking. And counteracting that is this what's called a imaginary force, I guess. Or some people say it's not a real force; it's a centrifugal force. It's actually center fleeing force. It's actually due to inertia. But basically, if we are traveling around in what's called uniform circular motion, that means that the speed at the of the object will be constant, and the angular velocity, or the rate of change of the angle with respect to time, will also be constant. So let's just have a quick look at a bit of an example. Okay, well, here we have our minions. They're both sort of going to be traveling in a circle in a minute. They're sitting on the radius, and like an extension of the radius, I guess, on the outside there. But let's have a quick look. Okay, GeoGebra automatically gives them what's called a uniform angular velocity, actually, and which one is traveling the fastest, which one has the greatest speed? I don't know if you can see it, but the one on the outside is a bit blurrier. It's a bit hard to see, actually. But the idea is that basically the speed is going to depend on basically the radius times what's called the angular velocity. And we'll derive that in a little while. But basically, just a quick example, I mean, the rate of change of the angle with respect to time is called omega, okay, which is d theta dt. If I differentiate that again, I get the what's called the angular acceleration, which is d2 theta dt squared, or d theta dot dt, and or sometimes called omega dot, actually. Okay, the angular speed, or the angular velocity, is in fact really just omega. Okay. Now let's go back. Okay, so the first thing is we are going to now look at some examples on how to derive these. Okay, the first idea, I guess, is angular velocity. Now, what is angular velocity? Well, it has a SI unit of radians per second. Okay, it's given a symbol omega. It actually is d theta dt, or theta dot, sometimes written as theta dot. Okay, and which is basically just means that yeah, well, it's a change in angle over change in time. It's called angular velocity. Okay, now let's have a look at linear velocity. Now, linear velocity is, I'll just derive it here. Basically, let's see if I can get this pen to work. Just hold on. Okay, I've drawn a circle. Now, let's have a look over here. Okay, we know EF, that's the arc length, which is actually, you won't be able to see, it's got a little S on it. We know that that is equal to r theta by our work with radians. Okay, L is equal to r theta. In this case, S is equal to r theta. Theta is actually in radians. Okay, so r is just the radius of the circle. Okay, it's traveling. Now, okay, so the first thing is, what do we do? Well, we differentiate with respect to time. As you can see here, we get ds dt is equal to, if you like, d dt of r theta. Now, as a constant, therefore it's just r d theta dt. Now, d theta dt is just omega, and we know that from earlier that it's just radians per second. So we can see here v, the linear velocity, is r omega, or r theta dot. Now, this is the instantaneous linear velocity. Okay, and because we are traveling with, obviously, if omega is constant, then the linear, instantaneous linear velocity will be constant. We actually just say that the speed is constant if it's traveling in uniform circular motion. Let's have a quick little example. Okay, there's a bit of an example here about on the Earth. Okay, example 1. What is our linear velocity at a point on the equator? Well, it does change with latitude, but we're just going to pick the equator, make it nice and easy. We know v is r omega, and we know the radius of the Earth. This is, you can see here, quite a few, about 6,003. Oh, it's actually about 6,400 kilometers, but it's a bit more accurately 6.3 times 10 to the 6 meters. We know that the okay, what is the angular velocity? Well, we know it travels around to basically 2 pi radians in basically a day, 24 hours, just roughly. And you can see here It's about 7.27 times 10 to the minus 5 radians per second. Okay, so that gives us, if you use a v equals r omega, that we will have a linear, instantaneous linear velocity of about 462 meters per second, which is quite quick, 1660 kilometers per hour. A lot of people say, oh, hold on, if we're traveling that fast, shouldn't we feel it? Well, because everything is actually traveling at the same speed as us, all the things around us, we don't actually notice it. But if, say, for instance, we suddenly slowed down or we sped up, which we'll do in the next example, well, we certainly would notice it. And I'll give a quick example here that if you're actually in a car and you brake suddenly, obviously, you're going to hold on to your coffee. Okay, let's actually move on. Okay, tangential acceleration. So we're going to have a look at tangential acceleration. Okay, well, I've drawn the circle again. I sometimes find that these circles can be a bit tricky to draw. So what are we going to look at? Well, acceleration. Okay, there's different types of acceleration. First of all, we're going to look at what's called tangential acceleration. We can actually have angular acceleration as well. Now, first thing is, the tangential acceleration is a bit like a linear acceleration, I suppose, in a way. If v is equal to r omega, then dv dt equals r d omega dt. Okay, so that is that the tangential acceleration is going to be a subscript t. I might leave it off in a little while, that subscript, but at this stage it's just to indicate that it's tangential as opposed to normal. You can see over here, tangential at right angles to the radius and normal acting towards the center. Okay, and basically we basically have that the what's called the tangential acceleration, okay, is a subscript t is equal to r omega dot, which is r theta double dot. Now, if the actual angular velocity omega is constant, then obviously this omega dot is actually going to be 0. Therefore, there won't be any what's called tangential acceleration, and the only acceleration will be centripetal acceleration acting towards the center, actually, which is coming from the centripetal force. Okay, now. Okay, so let's have a look at the example 2. Now, this is, well, I discovered just recently about these gravitational waves. I thought we'll just say, okay, let's suppose for some unknown reason this a gravitational wave started to accelerate the Earth. Okay, I just made up some sort of acceleration about 1.2 times 10 to the minus 4 radians per second, which is pretty quick actually. But basically, using the radius of the Earth at 6.35 times 10 to the 6 meters per second, you can see here that the tangential acceleration turns out to be r times that acceleration, which turns out to be about 762 meters per second, which is fairly rapid acceleration actually. So I just did a few calculations that if we're going to have to hold on basically, but the trouble is after about 10.5 seconds we haven't got much of a chance because it's the crust and mantle and all sorts of things will be flying off into space and we won't have much of a chance basically. But if we get up to a speed of about 8 kilometers per second on the edge of the Earth, or the equator, then basically we sort of basically get flying into space. Okay, hopefully this will never ever happen, but it's just a bit of an example here. Okay, well, let's go through now the derivation of the what's called the centripetal acceleration, which is acting towards the center and the normal. Okay. Okay, well, the first thing to do is get the components. X is equal to r cos theta and y is equal to r sine theta. This is coming from the right angle triangle here, r being the radius and going through that angle theta. Now, hopefully we can get those components without too much trouble. I've actually differentiated them here. You can see here. I'll put them on there. But basically what we do is we differentiate these components with respect to time. And we just, because r is constant, we basically get that we've got to differentiate cos theta with respect to time. As you know, that's implicit differentiation. So we differentiate with respect to theta and then have a d theta dt on the end. Now, d theta dt obviously is just omega. So we do this with the x and the y. And we end up getting x dot and y dot components. If you can take a quick look here, this is the x dot is equal to minus r omega sine theta, and y dot is equal to r omega cos theta. Now, you can see I've actually put them in the diagram there. Now we're going to differentiate these again shortly. Okay, well we're now just continuing on with the derivation. Now, okay, so the first thing is we have to differentiate x dot and y dot with respect to time. Now, basically, we've got a couple of problems. Well, not really problems, but we've got a couple of things changing. Okay, so we end up getting, well, first up, x double dot. We've got to differentiate this with respect to time, and you'll see here, I've actually just assumed that omega is in fact constant here. But if you want the non-uniform version of this, you just have to use what's called the product rule here. I may actually go through the product rule in a later video, but for non-uniform circular motion. But at this stage, we're just going to assume that the omega or d theta dt is constant. That way, we only have to differentiate sine theta with respect to t. Okay, and we end up getting that, obviously, again, it's chain rule, or just differentiation depending on how you do these things. X double dot, okay, is going to be d minus r omega, because they're both constant for uniform circular motion. Okay, and then we get d theta sine theta, which is, as you know, is just cos theta by d theta to t, which is another omega. And this is where, or why we get the omega squares coming into this, because we end up getting, let's try to make this a bit bigger. Okay, alright, we do the same for y double dot over here, to get y double dot, and we end up getting, obviously, because it's minus sine, we end up getting that x double dot is equal to r, actually it's negative r omega squared cos theta, and y double dot is negative r omega squared sine theta, basically both acting in a negative direction here. You can see I've actually got the vector directions over here in the acceleration. Okay, so these are what's called the components here. These components here on the diagram, these are the, if you like, the x and y components of the acceleration. And obviously these will be for uniform circular motion, because you might remember we actually assumed that omega was constant. Okay, well I'm now going to try this pen again and just see if this is the pen will be okay. Let's just check. Okay, it's not too bad actually, it's working alright. Okay, so we now, I've dropped up to the subscript AN, but just to make life a little bit easier. But basically, if we quickly do a Pythagorean result on it, we'll end up getting that, you get the components, you know, a squared equals b squared plus c squared, Pythagoras, and then we expand them out, know that sine squared plus cos squared is 1, take the square root, we're assuming, okay, the positive square root in this case, and we get that the normal component is r omega squared. We also know that v is equal to r omega. That means omega is v on r. Therefore, we get this other version of, if you like, the normal component of the acceleration, or if you like, the centripetal acceleration. Obviously, the centripetal force will be the mass times this acceleration. So the acceleration is r v squared on v on r all squared, but that will simplify to just a equals v squared on r. Okay. So there's a couple of, if you like, versions of the normal acceleration. Centripetal acceleration, which is a is equal to v squared on r, and a is equal to r omega squared, just depending. Now, we'll just go through a quick example here. Okay. Now, let's have a look. Okay, we've got a 2 kilogram ball on the end of a 1.5 meter rope, and we're starting to swing it uniformly at 3 radians per second, which could be quite tricky to do, but for the sake of the example, we're just assuming we're giving it what's called a uniform angular velocity of 3 radians a second. Now we need to find the tension in the rope, okay, and what speed can it sustain if the rope is not so terribly strong. Basically fails at 100 newtons. Okay, well, we know that the tensional force in a string is a force, so it's equal to m times a, which is mr omega squared. Let's see here. And if you put this in, you can see the tension is just 2 times 1.5 times 3 squared, about 27 newtons. Okay, So that's not too bad. So at the moment we've only got 27 newtons tension in the string or rope. Okay, so we now have to try and work out what velocity it's going to fail at. But basically we know that, well, 100 would equal mv squared on r. We know the radius, and we can just have to work out what the velocity is. We know the mass as well. Then we can see here it's about velocity worked out to be about 8.67 meters per second, and it would basically, after that particular speed, it would fail. Now, this obviously means that since we're going to fail at a particular velocity, we can also work out what the angular velocity was at that particular linear velocity instantaneously, which is just about 5.77 radians per second. So basically, if we increase the angular velocity up to about 5.77 radians per second, we're going to obviously increase the forces on the basically in the rope, I guess you could say, and after that it starts to fail and it will break, and the ball would head off tangentially, actually. Okay, a bit like a slingshot idea. Okay, well, thank you for watching, and that's all for this particular video. We'll continue on with the conical pendulum next. Bye for now.